All right, Chem 1110 students, here is the last section of Chapter 9. It's pretty short and it's pretty straightforward, so let's just see if we can't get through this. So we're talking about the concentration of solutions, and it's something that we've touched on before. One of the most commonly used and most important ways of expressing concentration is molarity. And so it's defined as the number of moles of a solute per liter of solution. And of course, the solute is the part that you've dissolved in whatever your solvent is. And so to calculate molarity, you just put moles of solute over the liter of solution. And this little diagram shows us something we're all very familiar with. We can tell if something is more concentrated if there is a color difference between the concentrated and the less concentrated material. And that's all this diagram is trying to show you. So it's just saying that this is a concept that we deal with on a daily basis, looking at coffee or tea or a number of other things. So here's an example. Hopefully we'll get through all these in the Zoom, and if not, I will post the answers. But in this case, you have an aqueous solution of glucose, so it's like a sugar solution, and they want you to determine the molarity of 2 liters of the solution that contains 50 grams of glucose. All right, now molarity is moles per liter of solution, so you've got to change that 50 grams into moles, and you can do that because you know the molar formula or the chemical formula for the glucose, and you can calculate the molar mass for it. Then the volume of this solution that would contain 0.250 moles, and the number of moles that would be contained in a half liter. All right, moving on, we're going to talk about dilution. And this is a process of taking a concentrated solution and diluting it down in the same solvent so that it's less concentrated. And although this seems like a fairly mundane thing to talk about, it's something we do in laboratory work all the time. So on the left, what they're showing you is a very concentrated solution. It's very dark. And next to it, there's a 10 ml volumetric pipette. Those measure volumes extremely accurately, and they're taking 10 mils of the concentrated material and putting it, which is a liter, and putting it into 100 ml volumetric flasks. The flasks are also extremely carefully calibrated and highly accurate. What we're showing in the right frame there is a dilution series that goes from high concentration through a couple of intermediates down to a very low concentration. And this is something we do in the lab all the time. The most important takeaway from this is that the moles of the solute that exists, say in that 10 ml pipette, before the dilution is the same moles of solute after you dilute it. So you're moving that whatever it is, glucose, potassium permanganate, and you're moving a certain aliquot or a certain portion of it into another volumetric flask and just diluting it up. So you're changing the volume, you're not changing the number of moles of the solute. So here's another example problem. I give you a little bit more detail on this. So in an experiment, a student needs a liter of 0.400 molar potassium permanganate solution, and there is a 1 molar stock solution of potassium permanganate available. So the question is, how can this student make the 0.400 molar solution? So you can use that relationship that the moles of solute before dilution equals the moles of solute after dilution. We know that he needs 1 liter of 0.4 molar. We know that he can start with 1 molar And so we have written this equation where we have the molarity of the concentrated solution by the number of liters, so that could be volume of the concentrated solution, is equal to the molarity of the diluted solution times its volume. We plug in what we know. So the right hand is the solution that he wants to make. He needs a liter of a 0.400 molar solution of potassium permanganate. On the left, we show the stock solution. All we know is it's a 1.00 molar. And we can solve for that volume of concentrated material he has to use. And in that case, it's 0.4 liters or 400 mils. And so if you had to actually make this, he'd get a 400 milliliter volumetric pipette and fill it to the mark with the stock solution and then put it into a 1 liter volumetric flask and dilute it to the calibration mark with the solvent. Now, sometimes, in fact, quite often when we are doing work in the lab, we're really dealing with milliliters more often than liters. And so we just want you to realize that you can write this equation that is, concentration versus volume before and after dilution. They're equal. The number of moles is equal, and the volume could be in milliliters instead of liters because any conversion factor would cancel out. The other thing we want to talk about here is something called serial dilution, and this is where you're trying to make a series of solutions that are increasingly more dilute. So you prepare a dilute solution from the stock, you dilute a portion of that to make a more dilute solution. You repeat it as often as you need, because quite often for some analytical work you might need 4 or 8 standards. You just keep diluting. So here's another sample problem. You have a 12 molar HCl. This is what is usually considered concentrated HCl. It comes in great big gallon jugs, and you want to use it to make 250 mils of 0.125 molar HCl. So you're going to use that M1V1 equals M2V2. Molarity times the first volume is equal to molarity times the second volume. And like I say, hopefully we can go over that in our Zoom. And here's another one. You have a 2 molar stock solution of hydrochloric acid. You need 4 standard solutions, 1, 2, and 3, and 4. You want to do this serial dilution, diluting 10 mils of each solution to 250 mils. And they want you to determine the concentration of those 4 solutions and then find the number of moles of HCl in each one. Fairly straightforward calculations. Here's another one. They talk about the square bracket notation, and that is just saying, as I've mentioned before, if you put something in a square bracket, like the sodium plus ion at the end of this problem, that means concentration of. So that statement is the concentration of the sodium ion is equal to 0.124 molar. And then the last topic is just about gravimetric analysis. And it is a kind of analysis that uses mass that you can weigh. And it's extremely accurate because we can weigh things out to a very high degree of accuracy. And it only works if you are conducting a reaction that will go pretty much, complete or 100% yield. So here's a question. You have this 0.8633 gram sample of an ionic compound that you know has chloride ions in it, and some unknown metal cation, which is not particularly important. It's dissolved in water, and then you react it with silver nitrate. So what you're going to get, since there was chloride in the original sample, you'll get silver chloride. And they tell you get 1.5615 grams of that. What is a percent by mass of the chloride in the original sample. And so here's a little statement of strategy. You know the mass of silver chloride, you can get that off your periodic table, and from that you can get the percent composition of silver chloride. In other words, how much chloride would be in that precipitate. And all of that chloride was in the original sample. So once you determine what mass of chloride you have, you just compare it to your original mass of your sample and you can get the percent. And that's it for Chapter 9.